a signal f is band limited if there exists a positive integer n such that in this Fourier series representation, ak equals bk equals 0 for all k greater than n. In other words, there are only a finite number of terms in the summation that appear in the series. In numerical computations, we cannot work with infinite series, so we'll be approximating signals with band-limited ones. But that limitation is not necessarily a problem in practical applications. For example, there's an upper limit on the sound frequency that can be perceived by humans. So for audio signal processing, we can really limit ourselves to band-limited signals, though we do have to be careful to avoid a phenomenon called aliasing, which we will not be discussing here. One issue that arises in practical applications is that we often do not have the precise mathematical description of a signal. That means we cannot use the integral formulas to obtain the coefficients in the Fourier series representation. But what we do have is that we know the function values at various points. In other words, we can sample the function. So if this is the representation that we're working with, then a0 up to an together with b1 up to bn are unknowns, and there are 2n plus 1 of them. We let capital N denote this total number of unknowns. And we sample the signal at capital N distinct points within a single period. As a result, we obtain a system of capital N linear equations in capital N unknowns. For digital audio, typical sampling rates are 44.1 kHz, that is 44,100 samples per second, and 48 kHz. These are even numbers, whereas what we have here is odd. So this is something that we need to deal with, and we'll start this sampling at an even number of points later. So for now, we're going to sample at capital N equals 2n plus 1 points, and we're going to sample them evenly distributed within a period. So we define XL to be t times L divided by capital N. Recall that t is the period of the signal, and L ranges from 0 up to capital N minus 1. And so we sample f at x0 up to x sub capital N minus 1, and we'll denote the function value at xl by f sub L. And so this will be a linear system of capital N equations in capital N unknowns. Notice that the period t does not appear in the system, and that cosine and sine are evaluated at integer multiples of 2 pi over capital N, and that's precisely the angle in radians of 1/nth of the full circle. So we can solve this system directly, but it turns out that it is more convenient to pass over to complex numbers. And to that end, recall Euler's formula, e to the ix equals cos x plus I sine x. Using that, we can write cos x as e to the ix plus e to the negative ix, all divided by 2, and sine as e to the ix minus e to the negative ix, all divided by 2i. And with that, this can be written as this. Here, we have the exponentials e to the I 2 pi k L divided by capital N, and k ranges from negative n to n. This is taken into account in this summation for k equal to 0. Each of these will have e to the I times 2 pi kl divided by capital N, and e to the negative I 2 pi kl divided by capital N. Both are precisely captured by this for positive k as well as negative k. And now xk will be a complex number for k from negative n all the way to n. And so this is now a system of capital N linear equations in capital N unknowns over the complex numbers. And now we're going to do a bit more rewriting. So for that, notice that e to the negative I 2 pi kl divided by capital N is the same as e to the I times negative 2 pi kl divided by capital N plus 2 pi times L. And adding an integer multiple of 2 pi to the argument does not change the complex number. So this step is valid. And simplifying, we get this. So these two are equal. Next, we relabel x sub negative k as x sub capital N minus k for k from 1 to n. And we also note that capital N is 2n plus 1. So this here can be broken down into two sums. The second sum here is when k ranges from 0 to n. The remaining is for k from 1 to n, but the indices here are negated. And now this can be rewritten as x sub capital N minus k times e to the I 2 pi times the quantity capital N minus k times L divided by capital N. So we get this here. And we can rewrite the indexing. So as k ranges from 1 to n, capital N minus k ranges from capital N minus 1 down to capital N minus n. But capital N minus n is n plus 1. And capital N minus 1 is 2n. So these two summations are the same. And now we can put these two together with the index k ranging from 0 all the way to 2n, which is capital N minus 1. And so we obtain this. So FL equals this for all L from 0 up to capital N minus 1. And this is now a much nicer looking system to work with. So let's look at an example. Suppose that capital N is 3. We let omega denote e to the I 2 pi over capital N, which is 3. And the system will look like this. So there are 3 equations, one for each value of L. And if we write this out, it looks precisely this. So we can solve this for x0, x1, x2. And it turns out that there's a closed form solution. It's given by this. More generally, if omega sub capital N denotes e to the I times 2 pi divided by capital N, which is the nth root of unity, the system here has closed form solution given by this. And this is known as the discrete Fourier transform.